Okay, a quick summary here. We have a current along the x-axis. We have a loop of square loop sides A at distance B from the axis, this distance being B. Then we want to find the flux through the loop. First thing we want to do. Then we're going to want to do things with the loop, like pull it away and find the EMF and so forth. But right now we just want to find the flux through the loop in terms of these quantities. Right-hand rule tells us that the field comes out of the board on this side, goes into the board on this side. So here are the X's indicating the field out of the board, and the more widely spaced X's indicating that the field is decreasing as you move away from the wire. And of course we know that the magnetic field of the wire has magnitude 2K prime I over R. Okay, so what we do to figure out the flux through this loop, the magnetic field changes from one side of the loop to the other. And it's a reciprocal with the distance, and that's not a linear rate of change, so we're going to have to do an integral to figure out the flux through the loop. And in order to get a reasonable integral, just a slightly enlarged picture of the loop here in a different color, we could partition an axis perpendicular to X with its origin at X into smaller strips, or smaller subintervals, and for each subinterval we have a strip across this loop. So if a typical subinterval occurs at distance r star and has width delta r, then its area is going to be delta r times A, which is the width times the edge of the square. The sample point is r star, typical sample point in the interval. Then the representative approximation to the field is going to be 2K prime I over R star. Okay, that's a sample magnetic field strength. So that the flux is just going to be, this is just the magnitude of the flux. I'm not worrying right now about the sign of the flux. But the magnitude of the flux is going to be the magnitude of B times the area. The magnetic field is perpendicular to the plane of this loop, so it's just going to be magnetic field times area, which is 2K prime I over R star, multiplied by the area, which I said is delta R times A, the width and the length of the strip. The sum of those strips is going to be the sum of 2K prime I over R star multiplied by A delta R, R going from B to B plus A. That summation, as you shrink the delta R to 0, the R star gets squeezed down and just becomes an R in a process that you should understand. But we come up here and we find that this sum approaches this integral from B to A plus B of 2K prime I over R dr. And oh, heaven forbid, I've left A out of this whole thing. So we actually have an A dr. So everything I've done is going to need an A in it. Fortunately, I can insert an A here and an A here. Put a parenthesis, set of parentheses here to distinguish the A from the LN. So here's our expression for the flux. This whole thing wouldn't have the dimensions of area, of field times area, had I not put that in there. Okay, that factor A that I didn't insert is now here, 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 as now part of an A squared, because we've got the A times the negative A here and here. So I've got those in here. We'll do a unit check on this just to make sure everything makes sense. But having done that, we can proceed. Okay, so first place, the question is, if we move this thing away from the x-axis at velocity v, then what is the EMF at the instant the distance is y? So this distance, which was b in the original expression, is now y, so we're going to put the y's where the b's were in the original expression, and that's very straightforward. You can look back to the original expression and see how that works. But there's our flux. So, what's the derivative of our flux with respect to time? Well, the only thing that's variable here is y. Y is changing. So when we do the time derivative of this, the only thing that's not constant is y. So when we take the derivative, well, all this is constant, but we have y terms here and here in the natural log, so we're going to have to t derivative of the natural log of a plus y over y. And in a straightforward manner, the inner function being this, we take the derivative with respect to t of that, and then it's divided by this quantity because of the natural log. And just review the natural log if you don't understand that. We get this. Now the only derivative we have to take is the derivative in this expression. Y is the only thing that's changing again. So when we take the derivative here, we're going to use the quotient rule. Derivative of the numerator times the denominator minus the derivative of the minus the numerator times the derivative of the denominator, and that's going to be over the denominator squared. Just straightforward quotient rule. When we multiply all this out, derivative of this is just y prime, a being constant. The derivative of this is a plus y times y prime. Doing the arithmetic, we end up with this. The y prime y's subtract off, giving us 0, but we end up with a negative a y prime over y. And then multiplying that through here, the a times a gives us a squared. We'll put the negative out here. Again, we're being careless with the actual direction of the flux, whether the flux is positive or negative. In this case, I'm pretty sure it's negative. But anyhow, we have this expression. And now the only y prime term we have is here. So now what's y prime? We haven't actually taken the derivative of y with respect to t, but y is the distance from the x-axis. V is the velocity of this thing away from the x-axis. So that v is just y prime. Okay, y prime is the rate at which y is changing with respect to time, and that is the velocity. So we have this expression, and that's our EMF as a function of y.